Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. One-step methods, implicit and linearized Euler methods. The implicit Euler method is particularly useful for certain types of initial value problems where other methods might struggle. The method is called implicit because the current estimate, yi plus 1, appears on both sides of the resulting difference equation. The implicit Euler method sacrifices computational simplicity for robust stability, making it indispensable for stiff ordinary differential equations, i.e., the implicit methods in general remain stable even for larger step sizes. While it is a first-order accurate method, its unconditional stability and error damping justify its use in challenging problems where explicit methods falter. In the discretization process, the slope is evaluated at point xi plus 1, yi plus 1, and the first-order backward difference formula is applied for the first derivative. That is why it is also referred to as the backward Euler method. Rearranging the above equation leads to the following difference equation for the current step value, yi plus 1. Solving it for the current step value depends on the differential equation. If fxy is a linear function, the difference equation can be solved to give an explicit expression for the current step value, yi plus 1. Where f is a function independent of current step value. If fxy is a nonlinear function, if it involves powers of y, or in the argument of log or trig functions, etc., a direct explicit solution for the current step value cannot be found. Hence, a root-finding method needs to be employed on the following nonlinear equation to find z equals yi plus 1. The Newton-Raphson is often a preferred root-finding method to solve for the current step value, yi plus 1. Another thing to consider, sometimes people use fixed-point iteration for simpler nonlinear problems, but that's a type of root-finding too, albeit not as robust as Newton-Raphson. To employ the NR method, we first express the nonlinear, or discretized, equation as follows, where z is the variable whose zero is sought. Then the Newton-Raphson iteration equation is set up as follows. If fxy is a nonlinear function, the implicit Euler method can not only become more complicated but also computationally more involved and time-consuming due to solving a nonlinear equation at every step, in contrast to the explicit Euler method. A linearization technique may be applied to avoid solving nonlinear equations and simplify the process of solving for the current step value yi plus 1, which also enhances the efficiency of the method. Linearization of the implicit Euler method typically involves approximating the nonlinear function fxi plus 1 I plus 1 around the current iteration, or using a first-order Taylor expansion. Consider the Taylor series of fxi plus 1, yi plus 1 about its initial guess, xi plus 1, yi, which replaces the slope on the right-hand side as follows. Rearranging and solving for yi plus 1 results in the following explicit expression. The advantages of the method are: the implicit Euler method is a stable scheme that allows the use of large step sizes. It can be applied to both linear and nonlinear IVPs. The linearized scheme may offer some advantages if sufficiently large step sizes can be used. The disadvantages of the method are: The method has a first-order global error. For nonlinear initial value problems, the algorithm is a bit involved, and the CPU time can be significantly higher due to the implementation of a root-finding method at each step. Let us consider the following first-order initial value problem. We wish to use the implicit Euler method to solve the given IVP up to x equals 1. Obtain solutions for h equals 0.1 and 0.05, and compare the estimates with the given true solution. We start with the given first-order ordinary differential equation and apply the implicit discretization. Substituting fxy into the difference equation, we obtain. Since the IVP is linear, we can solve it for the current step estimate as follows. The initial value x0 and y0 are 0 and 2, respectively. For h equals 0.1, the abscisses run from I equals 0 to 10. And the numerical estimate for the current step is obtained as a recursive expression. Evaluating y1 gives 1.83, 33, 333. Using this value and evaluating y2 gives 1.69, 23, 077. Likewise, using the computed value of y2 and evaluating y3 gives 1.57, 14, 286. We continue this recursive process in the same manner for y3, y4, and so on until x equals 1 is reached. Notice that the true errors are in the order of 10 to the minus 2, with a mean value of 0.0385 for the solution interval. For h equals 0.05, the abscisses run from I equals 0 to 20. That is, the procedure requires twice the computation steps for the same 0 to 1 range. And the numerical estimate for the current step is obtained using the recursive expression, which is modified due to step size. Evaluating y1 gives 1.99909, which corresponds to the estimate at x equals 0.05. Using the estimated value of y1 and evaluating y2 gives 1.826870. This is the estimate for x equals 0.1. Using y2 and evaluating y3 yields 1.75. Similarly, using y3 and evaluating for y4 results in 1.68, which corresponds to the estimate at x equals 0.2. We continue this recursive process in this manner for y5, y6, and so on until x equals 1 is reached. The estimated results are tabulated in the presented output table. Notice that the true errors are also in the order of 10 to the minus 2, with a mean value of 0.0193 for the solution interval, which can be expressed as 0.386 times the interval size, which is just about half of that for the case h equals 0.1 since the implicit method is of first order. That is, the true error is directly proportional with h. That is all for now. See you next time with another topic. Bye.